Okay, so in this video we are going to work on determining the angular momentum for an assembly of rigid bodies, um, and the reason why we are solving this problem is because while angular momentum is relatively clearly defined for a given rigid body, especially about its center of mass, whenever we have an assembly of rigid bodies or a collection of rigid bodies, there can be some confusions in the calculation of the angular momentum of that assembly, and hence we are looking at that problem. Um, so the problem goes as follows. There is a sphere which is attached by a massless rod to a disc. The sphere is of mass m0 and it has a moment of inertia of j0. Since it's a sphere, the moment of inertia is the same in whichever axis you consider about the center of the sphere, and for the disk, so this is a sphere and this is a disk. For the disk, it has a mass of m1 and it has a moment of inertia of let me just check. It has a moment of inertia of so disk, its moment of inertia is IA about axis of symmetry, and it has a moment of inertia of I1 about transverse axis. Okay, so I1 is going to be the moment of inertia, for instance, about an axis going like this through the center, or an axis going like this through the center for this disk. About its axis of symmetry, the moment of inertia is IA. For the sphere, the moment of inertia is IO about any axis through center. Now, it is given that the distance between these two rigid bodies is L, and furthermore the center of mass is somewhere here, and the center of mass makes a distance of L0. This is the center of mass of the assembly. It makes a distance of L0 from the center of the sphere, and it is at a distance of L1 from the center of the disk. Okay, it is given that this axis, the one that I am drawing right now, is the axis of symmetry, of the assembly. Furthermore, it is also given that if we call this axis going through the center of mass and pointing upwards, if we call this axis, or if we call the unit vector along this axis as EB, then initially the whole system has got an angular velocity of omega b about this axis, about this axis EB. So we specify that whole system turns with omega b about axis EB. Okay, and then there is no other motion at the beginning. Now it is also given that at t equals 0, an internal torque between sphere and disk causes the disk and sphere to start rotating about the axis EA. Oops, sorry, this is EA. Now EA is this axis of symmetry. Okay, E sub A is the unit vector along the axis of symmetry of the assembly. So at the initial time there is an internal torque, so you can imagine that there might be a motor here which starts exerting a torque which causes the disk to go in to turn in one direction along the axis of symmetry, and the sphere then turns in the opposite direction but still along the axis of symmetry. And it is given that the torque causes omega t about the axis of symmetry, causes omega t causes omega t to be the relative angular velocity along EA. Okay, so omega t is the relative angular velocity along EA as a function of time. Initially there is no angular velocity along the along EA. So given this, what we want to do is we want to find out, so find two things. Number one, the angular velocity of disk and sphere as a function of time at any instant, let's say at any instant. And number two is the angular momentum of the assembly. Okay, so this is the problem statement, and so before we start the problem, we would like to just articulate some of the basics of angular momentum of a system of rigid bodies. So let us just quickly go over angular momentum for a system of rigid bodies. Okay, so this is best explained through a diagram. So let's consider let's say an inertial reference frame XYZ, right? and let's say that there is a rigid body or a system of rigid bodies. We are just showing two here. So let us say that this is the rigid body 1. It has a position vector r1, right, and it has a mass of m1, and let's say that it has some angular velocity omega 1 about a certain axis, and this is the center of mass of the rigid body 1. This is the origin O. Similarly, the ith rigid body has a position vector Ri. Let's say it has an angular velocity of omega I, and it has a mass of mi. Okay. Furthermore, let us say that the center of mass of this assembly, there are other masses that we have not shown for the sake of simplicity of this diagram. Let's say that the center of mass of this whole assembly is somewhere here as shown, and we draw a vector going from the center of mass to the ith mass, and we call that rho I. Similarly, we draw another vector going from the center of mass to the center of the first mass, and we call that rho 1. Okay. Furthermore, let's say that there is a vector that is going all the way from the origin to the center of mass, and let's call that rc. So a number of vectors, as you can see here. So rho I is the vector going from the center of mass to the ith mass, and rho 1 is the vector going from the center of mass to the first mass. In contrast, Ri and R1 are the vectors going from the origin to the ith mass and the first mass. Okay, so, and we have also given the angular velocities. So the idea is that the angular momentum of this assembly about this fixed point O is formulated as summation I equals 1 to n. So let's say there are n rigid bodies. Ri cross mi Ri dot plus summation I equals 1 to n I sub I dot omega I. Okay, so this is essentially saying that the net angular momentum of this assembly of rigid bodies consists of two terms. One is the moment of inertia of the individual rigid bodies about their center of mass. So this represents the sum of the angular momentum of each rigid body about their respective center of mass, considering their respective angular velocities. And then to add to that, this is the angular momentum due to the motion of the center of masses of the individual rigid bodies. R dot I is the velocity of the center of mass of the individual rigid bodies. So you can see this is of the rigid bodies with respect to themselves, and this is because of the motion of the rigid body, the center of mass of the rigid body with respect to the origin. All right. Now, if we want to express the angular momentum about the center of mass, that formulation is as follows. It is I equals 1 to n rho I cross mi rho I dot plus I equals 1 to n I sub I dot omega I. So this is the formulation of the angular momentum of the system of rigid bodies about the system's center of mass, and you can see the only change over here is the vector Ri getting replaced by rho I, where rho I is the vector going from the center of mass to the ith rigid body. Now, a couple of things to keep in mind. Although we have written this in the form of a dot product, and dot product is by definition a scalar, but this is not. So keep in mind that this is basically taking the moment of inertia matrix and multiplying it with the omega vector. So it gives us the I, j, and k, or the three components along the triad that we choose. Another thing to keep in mind is that when we calculate these individual moments of inertia, each rigid body may have its own body fixed frame, and so you may get the angular momentum of those individual rigid bodies about their center of mass in different triads, and so those triads will typically not be compatible. So when we solve a problem like this, we need to use some kind of rotation matrices if needed, if those triads are not compatible, so that you can express everything in terms of one set of unit vectors belonging to one triad. So that is something to keep in mind when we derive the angular momentum of a system of rigid bodies. In this problem, we bring this up because the angular momentum of the assembly that we are interested to find out we should clarify about the CM, that is the center of mass that is given over here. So that is so we want to find out the net angular momentum of this sphere and this disk about the system's center of mass, and because of that requirement, we are going to be actually using this second, or in fact the first one also works in this case, because the way the problem is defined, actually the center of mass is not moving, so O is actually the center of mass is actually a fixed point. But in any case, either of these two is applicable and gives the same result. Okay, so let us first formulate the angular velocities of these two rigid bodies. So for the sphere, let's say that the angular velocity of the sphere is omega s, and the axis system that we are going to choose in expressing the angular velocities, we want to keep the same triad, and so we are going to have EA along the axis of symmetry. We are going to use EB in this direction going upwards, and mutually perpendicular to these two we will have the unit vector EZ, which is going to be going let me just check, yeah, it is going to be going outwards from the page perpendicularly, and so you can see that the right-handed coordinate system would be such that EA cross EB is going to give us EZ. So essentially our cross product convention is going to be EA cross EB giving us EZ. So it is going to be this convention that we are going to follow whenever it's needed for us to do cross products. So let us first consider the sphere. The sphere initially is just turning about this EB axis, and at a given instant, arbitrary instant, once the torque gets activated, there is going to be an angular velocity along this axis of symmetry. So as the sphere and the disk, they rotate about each other, the axis of symmetry that is connecting the two is now going to have there is going to be an angular velocity about that. So this omega b so this angular velocity of the sphere is going to be omega b EB plus some angular velocity along the axial direction So let's call that omega AS. So this is representing omega, the angular velocity, in the axial direction for the sphere, and this is going to be in the EA direction. Now in the EB direction, the angular velocity is omega b, because the whole system is being turned by an angular velocity omega b. The whole assembly is being turned, so both the sphere as well as the disk have share that same angular velocities. Now with this, now let us write the expression for the angular momentum of the sphere about the cm, and when what we mean by cm is this cm. So let's write the angular momentum of the sphere about the center of mass of the assembly. So that is going to be going by this expression here. So it is going to be let me just check the expression. So I of the sphere times the omega of the sphere, so it's going to be the sphere is going to have I O omega b in the EB direction, and it is going to have an I O omega AS along the EA direction. Okay, so this is the moment of this is the angular momentum of the sphere about its center of mass, So that is the first term. So and then what we need to do is we need to do the rho cross mi rho I dot. This term needs to be done. So what is the rho I? The rho I is going to be a vector that is going to go from the center of mass to this point. Okay, remember that the rho I vector goes from the center of mass to the center of mass to the individual body. So in this case it's going to be negative L naught EA, right, cross then mass times the velocity of the relative velocity of this point with respect to this point. So the mass is the m naught, and what is the relative velocity? Well, if you think about it, the whole thing is turning like this about the EB axis. So the center, with respect to the center of mass, the center of the disk is moving up like this, and the velocity is L naught times omega b. So L naught times omega b, and this is going to be the velocity, and this is in the EZ direction. Let me check. Yes. And so what we get is the following. You see that here we have a cross product. EA cross EZ is negative EB. So what we'll get is IO plus MO LO squared, or M naught L naught squared, times omega b EB plus I naught omega AS EA. Okay, so that's that's the sphere's angular momentum about this center of mass. Now let's do a similar calculation for the disk. Now for the disk, let's denote the angular velocity by omega d. Omega d is going to be omega b EB, because the whole assembly is turning about the EB axis with an angular velocity of omega b. And then it will also have an axial angular velocity which we do not know, but we are going to represent it as omega d, or rather omega axial, omega a d. Okay, so it is omega axial for the disk, EA. And taking the same step forward, then the angular momentum of the disk about the center of mass of the assembly is going to be then I times this omega, which is going to be for omega b, it is the angular velocity of the disk about this axis, which we have given it to be I1. So it is going to be I1 omega b EB, and then it will have the angular velocity about the axis of symmetry, which is omega AD, and the axis of symmetry moment of inertia is IA, so IA omega AD EA. So this is the angular momentum part of the disk about its own center of mass, okay, using the symmetry axis EA and EB as the other transverse axis and Z as the other transverse axis. So that's the angular momentum about its own center, and then we need to put together the angular momentum due to the fact that the center itself is turning with respect to the center of mass of the system. Now we see that the center of the disk is at a distance of L1 and it is in the positive EA direction, so we have L1 EA cross M1 is the mass of the disk times the velocity. Now the velocity, if this is moving this way, the velocity of the disk is into the surface of the page, and it is L1 times omega b, and it is in the negative EZ direction because it is going into the page. Okay, so let's carry out this cross product and add these two. So when we do EA cross EZ, EA cross EZ, we are going to be moving in the reverse direction, so negative EB. So what we will have is I1 plus M1 L1 squared omega b EB plus IA omega AD EA. Now a couple of things that you can note between this and this is that as we are taking a very structured approach to find the angular momentum, and as a result of that we are getting this parallel axis theorem happening quite naturally. So here what you see is parallel axis theorem essentially. The same thing happens over here, but it's happening naturally as we apply the basic formulation for angular momentum about a point which is away from the center of each of the rigid bodies. So this gives us the angular momentum of the disk. Oh, I should put the arrow over here because it's a vector. The angular momentum of the disk and the angular momentum of the sphere about that common center of mass. Now let us add the two together because we need the angular momentum of the assembly. So therefore H total about the CM is equal to, let's add these. So we are going to have I1 plus I0 plus M0 L0 or M0 L0 squared plus M1 L1 squared times omega b EB plus we have I0 omega AS plus IA omega AD EA. Now one thing to note over here is that because we use the same triad to express the angular momentum about the common center of mass, we could easily add these two. If we didn't, then we would have to use some kind of coordinate rotations, so rotation matrices. So we averted that step of having to do coordinate rotations by using a common triad EA, EB, EZ to express all our vectors. Now at this point we are not done, because we don't yet know what are the angular velocities omega AS and omega AD. We know that these are the angular velocities in the axial direction. We don't know their values. So in order to find their values, we will do a quick analysis of the equation of motion of the disk and the sphere. So if you consider the equation of the sphere by itself, and if you consider, let's say you have, this is your EA direction, this is the EB direction, and that's the Z direction, EZ. You can write the Euler equation, equation of motion for the sphere about the EA axis, and what you would get is the following. You will get the moment applied in the axial direction on the sphere is equal to I of the sphere about the axial direction, which is IO, times the rate of change of the angular velocity of the sphere in the axial direction, plus omega this is not omega, this is I ZZ minus I YY. Well, I'm going to clarify this IYY. This is actually going to be, let me just write it as IBB times omega in the Y direction and omega in the B direction. Okay, so if you, I would urge you to go over a textbook, any textbook in dynamics of rigid bodies, where they discuss the Euler equations. This is one way of expressing the equation of motion of a rigid body, and this is in particular about the EA axis. There are two other equations that form the overall rotational equation, one along the B axis and one along the Z. I just chose the axial direction just to illustrate an interesting observation, which will lead us to finding out what this expression is and what are the different angular velocities, omega AS and omega AD. So we will find those out. Now in this case, note that this whole term is equal to 0, because IZZ is IO and IBB is also IO. Okay, so what we have is that the moment in the axial direction on the sphere is equal to IO times omega AS dot. Right, now if you take the disk, and again if you set the same set of triad axis, and if you write the Euler equation again, but now for this disk, you will see that the moment in the axial direction on the disk is equal to I about the axial direction, which we are calling as IA, times omega AD dot plus IZZ, this is the IZZ for the disk, minus IBB, this is the IBB again for the disk, times omega Y, omega B, omega Y for the disk and omega B for the disk. And again this becomes equal to 0 because this term IZZ and IBB are both equal to I1, and this we had specified at the beginning when we were solving the problem. These were the transverse moment of inertia. So this reduces to IA omega AD dot. Now in this problem it is given that there is an internal moment that is being applied that causes the disk to turn with respect to the sphere and vice versa. So if there is an internal moment, then we could say that the moment on the sphere and the moment on the disk are basically equal and opposite, right? Because if there is a motor that is turning the disk with respect to the sphere, then the disk itself, or rather the sphere itself, is experiencing an equal and opposite moment. So we implement that here. So therefore, since MAS and MAD are internal action reaction pair, therefore MAS plus MAD is equal to 0, right? And since that sum is equal to 0, therefore I naught omega AS dot plus IA omega AD dot is equal to 0. Okay, and what that means is that because I naught and IA are constants, we can say that I naught omega AS plus IA omega AD is equal to, the sum of these two is equal to I naught omega AS at time t equals 0 plus IA omega AD at time t equals 0. So this is just an integral of this differential equation. It is easy to integrate because IA and IO are just constants. Now we have this. Now we note that the initial velocities along the axial direction are both 0. That is the sphere and the disk. They don't have any initial rotation about the axial direction. They just have a rotation about the EB axis. And because of this, we can then conclude that IO omega AS plus IA omega AD is equal to 0. Now this is nothing but the conservation of angular momentum about EA. So in other words, we have taken a very structured approach to solve this problem, and instead of right away at the beginning just imposing that the angular momentum is conserved in the EA direction, we went through the process of deriving the total angular momentum about the common center of mass, and we then analyzed from the equations of motion the nature of the motion along the axial direction, the common axial direction for the two rigid bodies, and we concluded that because these moments are internal action reactions, so therefore the angular momentum along the axial direction is going to be conserved. So that is good, and so we go back. So let me just arrange these pages here, and so we then say that therefore H total about the center of mass is equal to, and I'm just going to put the original expression here, You see, this was the expression that we had, right? And now we can say that this term is equal to 0 because we just proved the conservation of angular momentum along the EA direction. Therefore, the net angular momentum is in the EB direction. It is given by I1 plus I0 plus M0 L0 squared plus M1 L1 squared times omega B EB. So that's the solution of part 2 of the problem. Now part 1 of the problem asks for the angular velocity of the individual disk and sphere at any arbitrary instant. So in order to find it, what we'll do is we will make the following we'll make the following observation. So we'll call this equation 1, and we will recall that it is given in the problem that at any given instant the relative axial angular velocity is omega t. This is given. So the functional form is not given, but it is, the problem specifies that you can assume it to be a certain omega, which is a function of time. Now we can then assume that the angular velocity in the axial direction between this and this is omega, so that will give us the second equation. One thing to keep in mind is that when there is a torque that is doing an action which is an action reaction pair, the object which has the lower inertia is, as you can intuitively guess, going to turn faster. So imagine that there is a motor that is mounted on a huge sphere, and it is trying to rotate a cylinder, and a much smaller cylinder or a disc. Then as the motor turns the disc, since the disc is small, it's going to start spinning, but the sphere is also going to spin because of the conservation of angular momentum, but its angular velocity is going to be lower because it has a larger inertia. So here, if we assume that the sphere has the larger of the two inertias along the axial direction, then we can say that from here we can say that at any given instant the angular velocity in the axial direction of the disk minus the angular velocity in the axial direction of the sphere is equal to omega. So the disk is bigger and the net relative angular velocity is omega, so we have this equation. So this is our second equation. So from these two, then we should be able to deduce the values of omega AD and omega AS. So you can, for instance, say that therefore I0 omega AS plus IA, and omega AD is going to be capital omega plus omega AS is equal to 0, which means that omega AS is equal to negative omega IA divided by IA plus IO. We just check the result. Yes. And similarly, omega AD is going to be capital omega plus omega AS, which is capital omega minus omega IA divided by IA plus IO, which is going to be omega IO divided by IA plus IO. So then these are the angular velocities in axial direction. So again, the conservation of angular momentum and the basic equation of relative angular velocities were used to find the individual angular velocities of the sphere and the disk at any given instant. So this is what I wanted to go over in this problem. Again, this is a problem on angular momentum of a system of rigid bodies. We analyzed the problem from the perspective of the basic formulation of angular momentum, and in developing the conservation of angular momentum equation, we went back to the Euler equation of motion of both the sphere and the disk about their axis of symmetry, and we were able to determine from there, or deduce from there, the conservation of angular momentum about the axial direction. So that's it. Thank you so much.